Another gas law that we are going to be discussing is Lussacs Law. Now this gas law, it talks about a different relationship relating to pressure and temperature. So this one is again a direct relationship. You can see here from the graph that as the temperature increases, the pressure increases. And as the temperature decreases, the pressure decreases. So that is a direct relationship. The conversions you're going to want to remember for this one: 1 atmosphere is equal to 760 millimeters mercury, and 1 atmosphere is equal to 101.325 kilopascals. Also, Celsius plus 273 equals Kelvin. So right here we have our formula: P1, or pressure 1, over temperature 1 equals P2 over T2. One key thing is when you're working with pressure, please make sure you convert to atmospheres so we are consistent with our formulas. So you always need to convert to atmospheres. But this is Gay-Lussac's law, the relationship between pressure and temperature. So that's the basic intro. This is Mr. Gay-Lussac right down here, good-looking guy. We are going to go and we're going to do some practice problems using this law. It's mostly just plugging in and then cross-multiplying like the other gas laws we've looked at so far. We're just going to do 2 practice problems. Look at these real quick. So just as with our other gas laws, you want to make sure you identify the different items that we are looking at. So first, determine the pressure change when a gas at a constant volume at 1 atm is heated from 20 degrees C to 30 degrees C. Now the first thing that we need to recognize is that we are in Celsius, and remember we want to measure here in Kelvin, so we're going to have to convert into Kelvin. So let's do that first. First we need to convert 20 degrees C, so we'll do 20 plus 273, and that equals 293 Kelvin, and that's going to be temperature 1. And then we'll do 20 plus, or sorry, not 20, 30 plus 273, and that's going to equal 303 Kelvin, and that is going to be our temperature. There we go, temperature 2. Our pressure 1 is going to be 1 atm, and we do not know our pressure 2. That is what we are solving for. We see that right here. Determine the pressure change when this occurs. So let's set up our formula here. Let's go back and make sure we have this formula. Let's bring that over to this screen so we have it on the screen somewhere. We'll set it down here for now. So our pressure 1 is 1 atm. Our pressure 2, we do not know, so we just put X right there. Our temperature 1, 293 Kelvin. Got to make sure it's in Kelvin. And our temperature 2 is 303 Kelvin. Again, make sure it's in Kelvin. Then we underline here, set up our ratio equal to right there. And then we are just going to want to cross multiply and solve. So we come here, you end up with 293x equals 303. And then all we got to do from there is divide, and you want to divide by 293. So divide by 293, divide by 293 right there. And so if we do 303 divided by 293, 303 divided by 293, you end up with 1.03. So we go 1.03 x equals 1.03, and we were solving for pressure, so that is in atm. Now, man, I keep hitting my elbow on that. Now, what we got to see here is that it's determined the pressure change. So we're going from 1 atmosphere to 1.03 atmosphere. That's a change of 0.03 atmospheres of pressure. So we want to note the change. So that is actually going to be our answer. So whenever you increase the temperature, it's going to increase the pressure, in this case just by a very small amount. Let's look at number 2 right here. We have a gas has a pressure of 699 millimeters of mercury at 40 degrees Celsius. What is the temperature at standard pressure? So let's identify quick. That right there is the first pressure we see, so that's going to be our P1. We do need to convert it to ATM, so that's important to note. Let's switch it up to blue. Yeah, that's good. Our first temperature is 40 degrees Celsius right there. And then it's asking what is the temperature at standard pressure. Now standard pressure, what is standard pressure? Well, if you look back at STP, standard temperature and pressure, standard pressure is 1.0 atm is going to be standard pressure. So that is an important thing to note. Now, are we in the units we need to be in? Millimeters Hg? No, we are not. If you remember to convert from millimeters Hg into atm, you simply do 699 divided by 760, and that is going to give you 699 divided by 760 is going to get you 0.92 atm for our pressure 1, and then 40 degrees Celsius plus 273 to get to Kelvin. So 273 plus 40, always good to check your work, 313 Kelvin. So this right here is our temperature 1, and this is our pressure 1. Now let's go ahead and work out the problem. So pressure 1 is 0.92 atm. Now what was our pressure 2? It's standard pressure, so that was 1 atm. Got that from here. It says, what is the temperature? So we're solving for temperature, and we're solving for it at standard pressure. You remember from our previous video that standard pressure is 1 atmosphere. Now, our T1 we identified right here, 40 degrees Celsius or 313 Kelvin. And then we do not know our temperature 2. That is what we are solving for. So we will set that up just like that, and then we will cross multiply and we will solve. So cross, so you end up with 313 equals 0.92x, and then you simply divide by 0.92 to get x by itself. This is really the same process we've gone through for each of the laws. So divided by 0.92 divided by 0.92, so 313 divided by 0.92. You end up with 340. Go to 3 significant figures. You end up with 340, and we're solving for temperature, and that's in Kelvin, so 340 Kelvin is going to be our temperature at standard pressure in this circumstance. If we were able to lower the temperature from 313 Kelvin down to 273 Kelvin, or down to the pressure from, increase the pressure from 0.92 atmospheres to 1 atmosphere. Sorry, I got temperature and pressure mixed up there. So that is how our temperature would change. You can see that as the pressure increased from 0.92 to 1, that the temperature increased from 313 to 340. So that sticks with our law of pressure and temperature increasing together. All right, well that is our final gas law, Gay-Lussacs law, pressure and temperature and their direct relationship. So good luck from here. Farewell.